Hi, I am Chih-Hao. I'm going to introduce our work, Convolution in the Cloud, Learning Deformable Kernels in 3D Graph Convolution Networks for Point Cloud Analysis. This is the outline of the presentation. This work focuses on point cloud analysis. So what is point cloud? Point cloud is one of the representations of 3D shapes. It describes every single point on the surface of objects, and each point is represented by the coordinates x, y, z, which is three-dimensional vector. The whole point cloud can be represented by an n×3 matrix. For each row in the matrix, it is a 3D position of single point, and n refers to the total point number. Our goal is to recognize geometric patterns of point cloud shapes. We propose a deep learning model for various tasks. For example, our model can classify this input point cloud as airplane instead of bag, car, or table. Also, our model can identify the part labels of each point in the point cloud. For example, the part label could be the body, wing, or engine of an airplane, which is colored and illustrated in the right of the figure. Why does this matter and why are we interested in this topic? 3D computer vision is required in various applications such as autonomous driving and augmented reality. Point clouds can be collected by 3D sensor LiDAR, which possess depth information, and it is useful for these applications, while images are RGB pixels, which don't have such information. In the following, I will going to introduce a related work, PointNet++. In this work, a point cloud is divided into several local regions. For example, we have 20 points in this region, and this region is represented by a 20×3 matrix. For each point, the three-dimensional coordinates x, y, z is mapped to a 64-dimensional feature by MLP, multi-layer perceptron. Applying shared MLP on all the points, the input point cloud is mapped to a feature map, which is a 20×64 matrix. After that, channel-wise max pooling is applied. This layer selects the largest number among all points for each channel. So by applying max pooling there, the feature map is mapped to a single feature vector, which is of 64 dimensions, and it describes all the geometric information of this local region. By applying this algorithm, a single feature vector, which is of 64 dimensions, is extracted from all the local regions. If we sample 500 local regions in the point cloud, for example, then the point cloud can be mapped to a feature map, which is a 500×64 dimensional matrix, which contains the feature vector of all the local regions. For classification task, several types of this operation can be applied to the input point cloud. It maps the n×3 matrix to a single global feature, which represents the semantics of this object, and the global feature can be classified with MLP, multi-layer perceptron, to a k-dimensional prediction, indicates the category of this object. For segmentation task, it can be interpreted as point-wise classification. By applying several types of this operation, the input point cloud n×3 matrix is mapped to a n×k output, where the k-dimensional prediction is assigned to every single point in the point cloud. Several related works directly use point coordinates x, y, z for feature extraction. They need point cloud normalization, which normalizes the input point clouds into a unit sphere, so their algorithm can work properly. And what's the problem? Their performance is vulnerable to object transformation, like shift, scaling, and rotation. Furthermore, normalization is not always work for all point cloud data. If there is a noise point outside the point cloud, then after the normalization, the main part of the point cloud is smaller than its regular size. So the method depending on normalization tricks might not work on these cases. Here are some illustrations. The leftmost figure shows the normalized point cloud objects, and the three figures on the right shows the point cloud object under different transformations, like shift, scaling, and rotation, respectively. Many previous works rely on normalization tricks. If the input point cloud is not normalized properly, their performance might be degraded, and it is not allowed in many real-world applications. Since 2D convolutional neural networks has outstanding performance for image data, and it has some nice properties such as shift invariance, we want to design a robust framework for 3D point cloud analysis. To do so, we have to define the local region and the kernel design. Next, we have to define the convolution operation between the two components to generate new feature maps. In the following sections, I'm going to introduce our work step by step. First of all, I'm going to introduce some basic components and ideas in the 3D graph convolution, such as receptive field, kernel, and the convolution operation. Next, with these basic components, we can construct 3D graph convolution layer and 3D graph max pooling layer, which shares the similar idea with the 2D convolutional neural networks. Finally, with the convolution and max pooling layer, we can construct models for various tasks, such as classification and segmentation. Now, let's start from the basic components in 3D graph convolution. In 2D cases, local patches composed of 3 by 3 pixels, for example, are used to represent patterns in local regions. Similarly, in 3D graph convolution, we define receptive fields to represent local geometry. The receptive fields is composed of central point, Pn, and its nearest neighbors in three-dimensional space. In the illustration, m equals 5, so there are total 6 points in the receptive field, including the central points. Each point P is represented by its three-dimensional coordinates x, y, z, and the feature f of P, which is c-dimensional. The direction between the central point and the neighbor point is very important in convolution operation, and it will be discussed later. Another fundamental component in 3D graph convolution is kernel. We define our kernel in a structure similar to the receptive field. One kernel has one central node and S support nodes. In the figure, S equals 3, so there are total 3 support nodes in the kernel. For each kernel point, which is colored in red in the figure, is represented by position k, which is three-dimensional vector, and the weight vector w of k, which is c-dimensional vector. Note that k and w of k are learnable in training, which means our kernels are deformable, and it will change its shapes to describe different local geometry in the receptive fields. Now we have defined the receptive field and the kernel. The next question is how to define the 3D graph convolution. The convolution value depends on the similarity between every pairs of the neighbor node in receptive field and kernel support in the kernel. Now we consider this simple case. We want to calculate the similarity between the neighbor node P1 and kernel support K1. Since they are in the same direction, they are similar, so the similarity value between them is high. On the other hand, the neighbor node P2 is in the opposite direction to the kernel support K1. They are not similar, so the similarity value between them is low. As a result, we define the similarity function as following. The first term is the inner product between the feature vector of neighbor node and weight vector of the kernel support. The second term is the cosine theta, where theta is the angle between the directional vector d and k in three-dimensional space. The similarity value of all pairs are computed accordingly. Then, how to derive the weighted sum? For each kernel support, the maximum similarity value among all neighbors is selected for aggregation. For example, for kernel support K1, the similarity between P1 is the largest, and the value 100 is selected for weighted sum. Next, we sum up all the maximum values and the inner product between the feature vector and weight vector of the central nodes. Finally, we define the convolution between the receptive field and the kernel. To demonstrate the robustness of the convolution, we analyze the property of similarity function. Since we use relative direction vector for calculation, the similarity value would not be changed by any translation, so the operation is shift invariant. Furthermore, we use the cosine similarity, cosine theta, for calculation, so the value of cosine theta remains the same under any scale, so the convolution operation is also scale invariant. With these fundamental components, we can construct 3D graph convolution layer and 3D graph max pooling layer. Similar to 2D CNN, 3D graph convolution layer is composed of several kernels, capturing different local geometry in the receptive field. By applying the convolution operation, the input feature vector is transformed to the output feature vector, where the dimension equals to the number of kernels. By applying the convolution on each point, a new output feature is assigned to every single point in the point cloud. Note that in this illustration, the gray rectangle represents the matrix of point coordinates, and the yellow rectangle represents the feature maps. The 3D graph max pooling layer can be applied with two steps. In the first step, we apply channel-wise max pooling on every receptive field, generating a new feature vector on each point. In the second step, we downsample the original point cloud into a smaller subset where the point number is smaller. Like 2D max pooling layer, this layer enables model to learn across different scales, enhancing the performance. With 3D graph convolution layer and 3D graph max pooling layer, we now can construct model structures for various tasks. To construct a model for classification task, we stack several convolution and max pooling layers in the model, generating a global feature, which is a 1024-dimensional vector, and it can be classified with multi-layer perceptron, generating the final prediction. The model for segmentation is constructed in a similar structure. The features from different scales are aggregated to enable learning from multi-scale information. By applying the shared multi-layer perceptron, a prediction can be assigned to every single point in the point cloud, generating the output prediction matrix. We evaluate the classification performance on the ModelNet 40. There are 40 object categories in this dataset, following the same settings in the previous works. we sample 1024 points from the object surface for training and testing. Our 3D GCN have comparable testing accuracy with much less parameters, indicating the efficiency of this method. Furthermore, we evaluate the classification performance under various shape transformations. This plot shows the results for random shift, random scaling, and random rotation respectively. For random shift and random scaling, we can see that the performance of previous methods degrades according to this transformation, while ours, denoted in the red line, remain constant, indicating the nice property of shift invariance and scale invariance. For random rotation, our model is also more robust than the previous methods. We evaluate the segmentation performance on the ShapeNet part dataset. There are total 16 objects and 50 parts in total. Some illustrations are shown in the right figure. All these parts are classified with a single model. We sample 1024 points from the object surface in the training and testing. Our model obtains comparable mean IOU performance in this dataset. IOU refers to the intersection over union. We visualize the comparison result of our method and two previous works. In the visualization table, the leftmost column shows the ground truth labeling for the part segmentation. The first column for each method shows the prediction under no shape transformation, and the shift column indicates that the shape is translated by 100 units, and the scaling column indicates the object is amplified by 10 times bigger. We can see that CVPR2020 and PointNet++ failed in both object transformation. On the other hand, our method remains the same prediction with this transformation, indicating the robustness of this method. We also visualize the kernel responses in the different layers. The red points indicate the larger response in the shape. In this figure, we can see that from layer 1 to layer 4, the red points move from the region of simple geometry to the fewer parts of higher semantics. As a result, we can conclude that the model can properly learn the semantics in the point cloud objects. In conclusion, we propose 3D graph convolution networks, which learns to recognize local geometry of point clouds. Graph max pooling is also introduced, allowing feature extraction of point clouds across different scales. 3D GCN is shift and scale invariant, robust to shape rotation, and achieves good performance with smaller model, which means fewer parameters. Our code is already available on the GitHub. Please refer to this link. Thank you for listening.